Welcome back to today's course session of the Discrete Maths 2 course. As I told you at the beginning of the lecture, with this part of this course session, we are going to change mode. We're going to leave the world of the theory of computation, which I love no ends, to enter something that for many of you will look like more like maths. So you will see numbers, you will have to calculate, all the nice stuff that you all know and love. Even though I actually prefer the other stuff myself, but I'm not going on record, only on YouTube saying that. Anyway, so this doesn't mean that this part is not important. It's supposed to give you an introduction to a field of mathematics called linear algebra that has plenty of applications in computer science. How many of you are following the linear algebra course at the same time as this one? So there are some, not many. So I hope to give some of you also something different from what you've seen in the other course. But I apologize in advance if you get bored. So welcome to the matrix. Probably many of you have seen this screenshot somewhere at some point in a previous life. And the thing is that matrices are one of the fundamental objects of studies in linear algebra. Now, what is linear algebra? If you go and look on Wikipedia or whatever your favorite source is, you will see a description like this. Linear algebra is, first of all, a branch of mathematics that studies things like vector spaces, which we are not going to study in this very introductory treatment of linear algebra, and linear mappings between such spaces, which we are going to see. The motivation for such an investigation comes from a very fundamental algorithmic problem, in fact. You want to solve a system of things called linear equations, which we're already going to meet today. And in fact, you've already met in your previous lives. Whatever math courses you followed from elementary school onwards, you have solved linear equations before. The way that we are going to approach the solution of linear equations and other topics in basic linear algebra is by focusing on two fundamental objects that linear algebra is about, namely matrices and vectors, which are also fundamental objects in programming, two-dimensional arrays and one-dimensional arrays. So this is all stuff that you know as programmers. In fact, some of the things that may look strange about linear algebra to mathematicians, for you computer scientists are just piece of cake because you're born with this. Now, why are we doing this? Oh, well, because there are plenty of applications of linear algebra in computer science. You know all the fancy things you see on the screen in computer games or wherever website you visit, or Photoshop, whatever, that's all linear algebra. Under the hood, there is linear algebra. Whenever you do a web search using Google, how many of you have done web searches using Google? I'm sure quite a few of you. All of you. If you haven't, then there's something strange. Well, how can Google spit out such an accurate ranking of answering the query that you pose? And the query might be like, where is my next girlfriend? And then sort of Google, or boyfriend, whatever you like. And Google will answer and give you even a ranking. Well, there is linear algebra inside. Google Translate, there's linear algebra inside. Google has developed algorithms that can give captions to pictures automatically. It's like a Google Translate from pictures to natural language. Linear algebra inside. Coding theory. We want to send information out in such a way that if there are errors in the transmission, we can actually still decode the information. Now, how many of you have seen an LP? Or played an LP? Yeah, some of you have. Yeah, not everyone. Well, I mean, have you ever asked yourself why, if you scratched an LP, most likely than not, it would not play anymore. Whereas if you scratch a CD, you can still play it, unless you really scratch it badly. That's because in the CD, there is error correction. In the LP, there was no error correction. You scratch it, you get chi-chuk-chutum, chi-chuk-chutum. Unless that was the industrial music you were listening to, that's not what you expected to hear. So all of this stuff and more have linear algebra inside. So that's by way of motivation. Now, of course, your motivation is to pass the exam. So let me give you some other motivation in the form of learning outcomes, linear learning outcomes, because they are in a linear list. So if you want to figure out whether you know the linear algebra you should know to pass this course, cross all those things. Now, those are skills. They are all skills. So how do you get to achieving those skills? You practice. Remember the samurai motto? The more you sweat in training, the less you bleed at the exam. Well, practice. Do examples, do exercises, not just those in the assignments. All those that I said to you, do them. That's the only way. End of commercial break. Now we get to linear algebra. Any questions about what I expect you to do? I guess no. You know it already. But you know, repetitions sometimes do help, especially me. So I told you that linear algebra has been motivated by the study of the solution for things like linear equations. Here's a silly example to motivate linear equations in real life, whatever real life could be real for you. So these days, most people don't want to eat carbohydrates. Don't ask me why. But anyway, there is this low-colvetni Livsstil trademark diet, very popular, especially with women or whoever else who doesn't want to eat carbohydrates. So there you are. Suppose you want to combine, you want to have the perfect diet for this LKL trademark lifestyle. So, and for some reason, this diet should contain 133 grams of protein and 93 grams of carbohydrate. That's, of course, way too much for any ordinary human being. But there you are, I'm old-fashioned. And you want to eat fish and corn products. Now, suppose fish contains this much protein and this much carbohydrates, and corn contains this and that. How much fish should you eat every day, and how much corn products should you eat? Of course, you can guess. I mean, we are scientists, we don't guess. We write a system of equations where the variable f stands for the amount of fish you need to eat, and the variable c stands for the amount of corn products you need to eat. And you set up the equation that says, okay, 70% protein from the fish, 3% proteins from the carbohydrates should sum up to 183. Which is the amount of proteins that I need, or you need. I don't. According to my son, I would need several thousands of grams of proteins, but that's another matter. That's the equation that tells you how much fish and corn products you should eat to get to your fantastic upper limit of 93 grams of carbohydrates. Then you eat a sneaker and you just kill off everything else. But that's another matter. So that's a system of two equations, which are linear equations. And the questions that we are going to address, and in fact, I think you've solved zillions of these equations in your life so far, especially if you're into this diet. Well, not only, especially because people told you to solve them for no apparent reason. So these are linear equations. How do we solve them? That's a fundamental algorithmic problem, because it's an algorithmic problem. We are computer scientists. We don't want to solve them ourselves by hand, God forbid. We want to program a computer to do it, even though at the exam, unfortunately, you will have to solve them by hand. And it would be as small as this one, perhaps slightly bigger, but not that much bigger. So these are questions that we are going to address. And to address them, I need to introduce a little bit of terminology. So let's introduce it. In the example that I gave you before, there were two variables in those equations, F for fish, C for corn. In general, you can have any number of equations, of unknowns, of variables. And let's call them, boringly, x1, x2, xn. This may be boring because we usually want to use more descriptive names for variables in our programs or in our systems of linear equations, but it actually is going to be helpful because we want to put these variables in some order when we create matrices and arrays. They have an order to them. So what is a linear combination of these variables? A linear combination of these variables is nothing but an expression like this one, where A1, A2, A3, AN are numbers. In this version of the linear algebra material that we are going to have in this course, numbers will be real numbers. But they don't need to be. They can be complex numbers, and in fact, they can be bits, 0 or 1, which is our favorite thing, isn't it? Then, of course, if these are bits, you need to decide what is multiplication and what is plus. But for the time being, let's assume that we are dealing with real numbers. So the variables range over real numbers, and the coefficients, the constants, A1, A2, A3, the multiplying coefficients are also real numbers. Now, what is a linear equation in the variables x1, xn? It's nothing but an expression that equates a linear combination of these numbers, of these variables, with a constant d, which is a real number. So, for instance, the thing that we had before is a linear equation. We had two linear equations. Why? Because here the variables are f and c. These are the multiplying coefficients, and this is the constant, 183 in this case. Now, whenever you have an equation, you want to solve it. What is a solution? A solution to a linear equation like this one is a tuple of real numbers that satisfy the equation when you plug it in for the variables. So S1, S2, Sn, a tuple of real numbers of length n is a solution to this equation if A1, S1 plus A2, S2 plus blah, blah, blah is going to be equal to D. I've already given you examples. So do you need more examples of this stuff? I'm asking you. That's why there is a question mark there. Okay, so
like D would be like what was given in the earlier example.
Absolutely. The question is D would be the given, sort of like 183 or 84 or pi or square root of 2 or whatever you want your level of carbohydrates to be. I don't encourage you to try pi, but you can always try. Now, what is a system of linear equations? A system of linear equations is nothing but a list of equations. In our previous example, we had two equations. You can have any number, one or more. Now, what is a solution to such a thing? Well, a solution is a vector of real numbers that solves all of the equations simultaneously. Okay, so you should solve the first one, you should solve the second one, you should solve the mth one. Okay, in our previous example, a solution to this system of equations here would be an amount of fish and an amount of corn products that would allow you to fulfill your need for carbohydrates and your need for proteins at the same time. That's what the solution is. You want to solve them all. And I resisted the temptation of naming the Pokemons here. Actually, I didn't. Sorry. Okay. Last bit of terminology. A system of equations is consistent if it has at least one solution. Otherwise, it's inconsistent. Okay, systems of equations can have solutions or they might not have them. If they have, they are consistent. If they don't have them, then we will see later on that they may have only one solution or infinitely many. So let's look at an example, shall we? Because real teachers do examples. So let me be a real teacher for once. Here's a very simple example. Two equations in two variables. Is this a linear system of equations? Yes, it is, because you have two linear combinations of the variables x1 and x2, which are equated to constants. Just for me, bye-bye sets. If I write something like this, is this a linear system of equations? Somebody said no. Why not? Because there is an x squared there. This is not, let me use red here. This is not a linear combination. Not a linear combination of x1 and x2. A linear combination has the form a1 x1 plus a2 x2, where a1 and a2 are constant. Okay, so after all, it was useful to ask this question, just to clarify what a linear combination is. So whenever you see an x squared, you say, spider sense is tingling, that's not linear. And of course, there's nothing holy about the square there. It could be cube, fourth powers, you name it. A half, square root, cube root. These are not linear. Fantastic. Okay, so how would you solve such a system of equations? Okay, one of your colleagues is saying using matrices. But in fact, I'm pretty sure that you've solved them before at high school, for instance, or even earlier, without using matrices. So you would just do elimination. You would just say, okay, the second equation tells me that x2 is equal to 6 plus x1. I substitute that in the first equation. I figure out what x1 is, and then I substitute the result back, and I get what x2 is. But somehow that's how we humans do stuff. And we don't want to work, do we? We want to feed linear equations to machines so that they can actually spit out the answer for us, if there is an answer. Or if they can tell us what are all the possible answers. Okay, so how do we do it in general? Well, before we do the general thing, let me ask you something that people who have a geometric feel to it might like. What kind of geometric object is the set of points in the xy plane that satisfy an equation like this? It's a line. It's like Frankenstein. It's alive. No, it's not alive. It's perhaps alive, but it's a line. Okay, why? So, yeah, thank you, Luca. So let's try to write this thing. So I said 3x plus y is equal to 2. Okay, so now let's make it bigger. I did write it big. So, thank you. There you are, that's x, that's y. Why is this a line? Okay, so when x is 0, y is 2. Okay, so when y is 0, x is, so if y is 0, so you get 3x is equal to 2. So x is 2/3. You just divide by 3 both sides, and you get 2/3. Okay, so let's say it's somewhere here. Well, this thing is actually all of the points. Yeah, so this is supposedly a line. Unfortunately, I'm not Michelangelo, so straight lines turn out to be not so straight when I draw them. But that's what this is. It's a collection of all the points on this line. They all satisfy this linear equation. So if somebody tells you how many solutions does this linear equation 3x plus y equal 2 have, your answer would be how many? Infinitely many. All the points on this line would satisfy the equation. Okay, so let's now assume that I add to this another equation that says x plus y is equal to 0. Or let's make it minus x plus y, just to simplify your life, equal to 0. That's also a linear equation in the variables x, y. And what does it look like? What line does it describe? Well, let me write it slightly differently. Y is equal to x. So it goes through the origin, because 0, 0 solves that. It goes through 1, 1. So it's the line that goes up 45 degrees, isn't it? Oops, sort of 45 degrees. So that's minus x plus y equals 0. So if I now ask you, how many solutions does this system of equation have? Your answer will be, it should be a pair of numbers that solves both the equations. If it solves the red equation, it must be on the red line. If it solves the blue equation, it must be on the blue line. So it must be on both lines. And there is only one point on both lines, and it's this one, which you can figure out what that is. Okay? So that's an example, a sort of a system of linear equations is in two variables is nothing but a collection of lines. If these lines intersect, then they intersect at one point, and that's the solution. But these lines might not intersect. So for instance, if I have a green line here that says that goes parallel to this one, and it goes through the point 1, 0, that will never intersect the blue line. So if you have a system of equation that consists of these two lines, then there will be no solution whatsoever. So what lesson have we learned? The following thing. The solutions of a system of linear equation in two variables are the points that lie on all of the lines. They can either be one solution when all the lines intersect in exactly one point, no solution when you have parallel lines, and infinitely many solutions when the lines are all one on top of the other. They're all the same. So that's a trichotomy that you will see applies basically to all kinds of systems of linear equations, even in more variables than 2. Such systems of linear equations may be inconsistent, that is to say, they have no solutions. They may have only one solution. That's the amount of fish and corn product that you actually have to eat in order to fulfill your needs. Or they may have infinitely many solutions. You have a degree of freedom on how much fish and corn products you actually eat. In fact, a lot of freedom, infinitely many possibilities. But then you need to choose, and that's hard. Then perhaps you will want to reduce the cost of your diet by choosing the one that costs the minimum amount. And that's also combinatorial optimization, which is based on linear algebra and convex sets and stuff like that. So it's also got to do with extensions of the material that we cover in this course, this part of the course. Okay, fantastic. As humans, we can draw pictures, but machines don't draw pictures. Machines need algorithms. And in fact, these algorithms have to work for any number of equations, so in any number of variables. In fact, even us, if we were to solve a system of equations in n variables, we would not draw lines in n-dimensional space, do we? Already two-dimensional space is too difficult for me. Three-dimensional space is way too difficult for me. Four-dimensional or five-dimensional or n-dimensional space is something I'm not going to ask you to draw. So here's a system of equations in 3 variables with 3 equations. How can we solve it in a way that can be generalized to any number of equations and variables? Fortunately, somebody devised algorithms for us to do that. And this somebody is a guy by the name of Gauss, together with a pal by the name of Jordan, or Jordan, because I think he was French. So what is the idea? Here's the recipe. It's a recipe for 3 because these are 3 variables, even though San Valentine is approaching a bit, but anyway, it's a threesome. 3 variables, 3 equations. Okay, so what is the recipe? You just follow steps in order to reduce your input equation to a form that is easy to solve. Now, of course, easy to solve is in quotes because we need to define what it means for an equation to be easy to solve. But you can imagine, for instance, that an equation that has been reduced to the form x equals 3 is easy to solve. Why? Because it's already solved. You know that x is equal to 3. You don't need to work. So how do we do it? Here's the recipe. Surprisingly, perhaps not, it consists of 3 elementary operations. That's why it's a recipe for 3 people. It's a threesome. So what is it that you do? You're allowed to do the 3 following steps. The first one is purely cosmetic. A system of linear equations, the solution to a system of linear equations does not change if you swap the order of the equations. That's absolutely immaterial. It doesn't really matter if I write this first equation first or I write it last. The solution of the system of equation does not change. A transformation that we want to apply to systems of equations in order to solve them should always have this property. Whenever you apply it, you should not change the set of solutions of the equation that you started from. Exchanging 2 equations does not change the solutions. What else can you do? You can multiply one equation by a non-zero number. So for instance, I could multiply here the first equation by 1/3. And the result would be x3 equals 3. Which sounds like a desirable result to get, because at that point we know what x3, the value x3 should be in a solution. Now, two questions. I claimed that this should not change the set of solutions. Second question, why is there this non-zero number in red? Or at least non-zero is in red, or it should be. I'm colorblind, amongst other things, so forgive me if I don't see red and black. Okay, so let's see first of all why this doesn't change the solutions. We are going to do it for a single equation in two variables, but then this generalizes. Thank you. So suppose that I have ax plus by is equal to c. And suppose that the vector s1, s2 is a solution. These are two real numbers. Okay, what does this mean that this is a solution? This means that a times s1 plus b times s2 is going to be equal to c. That's what it means to be a solution. That's my solution vector. Now, what I claimed was that I could actually take this equation here and multiply it by a non-zero number without changing the solutions. Okay, so let's do that. I multiply left and right of this equation by some number d. Okay? What I expect is that S1, S2 is still a solution. Let's check it. I plug S1 for X and S2 for Y. So what is it that I get? But hey, I've seen this thing before. What is it equal to? C. Bingo. S1, S2 solves the equation, which is what I wanted to argue. Now, why do you think it would be a bad idea to multiply that equation by 0? Why is it not allowed? Absolutely, your colleague is saying if you multiply that equation by 0, you just throw it away because it becomes 0 equals 0, and then that's always true, so you just throw it away. In that way, you modify the set of solutions because you've removed one of the constraints that you had before. Absolutely. So that's why you're not allowed to do it. So, for instance, if we go and look at this and we say, oh, let's multiply both sides of this equation by 0, then you remove it because it becomes 0 equals 0, and all you're left with is the constraint about the carbohydrates. Ha! Terrible. You were only interested in the proteins, and now they've disappeared. Good for you. Good for your liver, actually, but that's another matter. Okay, so what is the third thing that we can do? We can add a multiple of an equation to a different one. What does this mean? For instance, this means that I could multiply this equation here by, say, -3 and add it to the second equation. I could do that. This doesn't change the solution space. And I encourage you to check this at home. What I want to ask you now is, why is it important that you actually add a multiple of an equation to a different one and not to itself? In general. In general, this is a dangerous thing to do. That's why you're not allowed to do it. For special cases, in some cases it doesn't harm, but in general it's dangerous. Absolutely, you can actually, if you were allowed in general to add a multiple of an equation to itself, you would be able to multiply an equation by 0. Why? Because what you could do is say, I take this equation, I multiply it by -1, and I add it to itself. So what I get is 3x3 minus 3x3, 0. 9 minus 9, 0. That's essentially, I have implemented multiplication by 0, which I said is disallowed. That's why, in general, you're not allowed to do that, because you could change the collection of solutions to your system of equations if you were allowed to do it. So these are called elementary operations. They are called elementary because they are really elementary, aren't they? You have even done them at elementary school. You exchange two different equations. You multiply one by a non-zero number. Note, non-zero. Never multiply by 0. You add the multiple of an equation to a different one. Note, not to itself. By using these operations, you are actually able to turn any system of equations into one which is easy to solve. Shall we do an example? Let's do it. And since we have an example on the slide, let's use it. Then next time around, we will actually see how to represent these operations using matrices. So we have the first equation says 3x3 is equal to 9. The second equation says x1 plus 5x2 minus 2x3 is equal to 2. And the other one says 1/3 of x1 plus 2x2 should be equal to 3. Yep, that's not what I wanted to do. So let's turn this into a system of equations which is easy to solve. And I'll do some steps just because they are the steps that people do when they are using matrices. Okay? So first of all, why don't we swap the third equation and the first one? So that I have x3 where it should be, right at the bottom. I don't like x3. So I swap 1 and 3, where 1 and 3 mean equation 1 and equation 3. So what is it that I get? I get 1/3 of x1 plus 5. Sorry. Plus 2x2, that's equal to 3. The second one has stayed where it was. And my beautiful 3x3 has gone here. Okay, now we do what seems reasonable in order to get the value of x3. We divide the last equation, or multiply it by 1/3. That is to say, we divide by 3. Okay, so we are going to do 1/3 of let me now write R3 for the third row. So that if I write 3, then it looks like something odd. Okay, so what is it that I have? I have 1/3 of x1 plus 2x2 is equal to 3. You can see how boring that is, and that's why we want machines to do it for us. This is called the hand simulation of an algorithm. Okay, hey, now we know the value of x3. So this equation is easy to solve. It's solved. So one thing that we could do now is to use this information to simplify the second equation. This is what you would do manually, but in fact, this is not an elementary row operation per se. An elementary operation actually says, okay, now I want to get rid of the x3 here. How do I get rid of this x3 in the second equation? Okay, so we can add to the second equation minus 2 times the third. So what I would do, and I think I will sort of let you continue afterwards at home. So I'm going to take minus 2 times the third row, and I add it to the second, 2 times, not minus 2 times. 2 times the third row, and I add it to the second one. If I do that, I will have removed the x3 there. So first equation remains unchanged. I'm not going to write it. The second equation becomes x1 plus 5x2. Now the minus 2x3 disappears because plus 2x3. And so I have 2 times 3, 6, plus 2, 8. That's what I get for the second equation. And I know that x3 is equal to 3. Now, by continuing this process, you will want to get rid of the 5x2 here, so that, or of the x1, depending on how you choose to do things, so that eventually you will actually get to a form where you will have x1 is equal to number, C1, x2 is equal to number, C2, and x3 is equal to 3. That's what you want to get by applying some number of operations, which we know is denoted by star. 0 or more operations. And you want to get to something of this form. That's, of course, simply easy to solve because it's already solved. So what we are going to see on Tuesday is how matrices actually can help us in implementing this process. Any questions?
Will there be more matrix multiplications?
The question is, will there be more matrix multiplications? Yes, there will be more matrix multiplications. It's a fundamental operation. Well, you will have to multiply matrices, some matrices, but you know, I mean, machines do that for you, so. It's not really about multiplying matrices.